All right, let's talk about something that sounds super complex, but is actually a genius solution to a huge problem in crypto. It's called Anticone Finalization Depth. Now, I know, it's a mouthful, but this is a groundbreaking idea for a whole new type of blockchain, and it tackles some of the biggest hurdles holding the technology back. So let's dive in and figure out why this is such a big deal.
So first, to really get what's going on, you've got to understand the two main ways to build a blockchain. On one hand, you have the traditional linear chain. Think of it like a single-track railway. Every train, or block, has to follow the one right before it. It's a strict, single-file line. It's simple, it works. But then you have a DAG, a directed acyclic graph. Now this is more like a massive, bustling train station, with dozens of parallel tracks. Blocks can be created side by side, all at the same time, forming this incredible, interconnected web. This parallelism is the secret sauce for unbelievable speed. But, as you can imagine, it also opens up a whole new can of worms when it comes to security.
So, here's our game plan for today. We'll start by looking at why having many paths is such a big deal. Then we'll dig into the very specific problems that creates. After that, we'll introduce the new security model designed to fix it, look at the rulebook that makes it all work, and finally, talk about the amazing scalability payoff that makes all this effort totally worth it.
Okay, first up, one chain, many paths. The simple fact that blocks can exist next to each other in parallel is a fundamental shift in architecture. And because of that, it forces us to completely rethink how we approach blockchain security from the ground up.
And this leads us straight to the core issue, what we're calling the parallel block problem. You see, when blocks are being made in parallel, it creates a kind of uncertainty that you just don't have in a simple one after the other chain. It raises a tricky question. How in the world do you handle blocks that are neither in the past nor in the future of each other?
And here we get to the key term for today, the anticone. Let's go back to our train analogy. Imagine you're sitting on your train. The anticone is all the other trains on the adjacent tracks. They're not ahead of you and they're not behind you. They're just next to you. In a DAG, this group of parallel side-by-side blocks is the anticone, and it's the source of all the unique challenges we're about to explore.
This brings us to the first major headache, parallel uncertainty. What happens if a parallel block gets delayed on the network? How does the system ever know for sure that the set of parallel blocks, the anticone, is complete? A block that's just running late could suddenly show up and potentially change everything.
And it gets worse. This is what you could call temporal ambiguity. A bad actor could, in theory, create a block, hold onto it, and then release it at the perfect time to cause chaos. So the big question is, at what point can you finally say with confidence, okay, the past is settled, it's locked in?
And look, all of this, it boils down to one massive deal-breaking issue: trustless verification. If you can't be sure that the history is truly final, then anyone new who wants to join the network would have to download the entire blockchain history. We're talking potentially terabytes of data, just to be safe. That would absolutely kill decentralization. It would make it impossible for the network to grow. There has to be a way to prove, without trusting anyone, that old data is finalized and can just be ignored.
So, what's the fix? Well, the solution to all these problems is a completely new kind of security, one that's built specifically for this parallel world. And that's Anticone Finalization Depth. It's a mechanism that gives a rock-solid mathematical guarantee that an anticone is closed for business, permanently.
So here's the really crucial point. Anticone finalization takes the security we already know and trust from proof of work, the whole idea that rewriting history gets exponentially harder and harder the further back you go, and it applies that same brutal, unforgiving math to this new DAG-specific problem of locking down those parallel blocks. It's not about making an attack literally impossible. It's about making it so ridiculously, astronomically improbable that for all practical purposes, we can treat it as impossible.
And this table just illustrates the concept perfectly. I mean, think about it. Is it theoretically possible for a meteor to hit you right now? Yes. But you don't walk around wearing a helmet 24/7, right? Is it theoretically possible for someone to guess your bank password? Sure, but you still trust online banking. The probability is so vanishingly small, we all just treat it as zero. That is exactly the kind of security we're talking about for closing off an anticone.
Okay, so this sounds great in theory, but how does the network actually enforce this security? It's not magic. It's a really clever set of rules that are baked right into the network's consensus protocol. This is the Anticone rulebook.
You can think of this guarantee as a kind of security recipe with a few key ingredients. First, you've got standard chain stability, which just makes sure the main path is secure. Then, there's something called a merge window, which basically sets a strict deadline for how late a parallel block can be. If it's too late, the network just ignores it. Simple as that. There are also strict limits on how big an anticone can even get, which stops things from spiraling out of control. And finally, you add in some mathematical safety margins, just in case of a worst-case scenario. Put it all together, and you get this incredibly robust, multi-layered defense.
And these ideas are enforced by 3 golden rules. If a block breaks any of them, boom, the network just throws it out. The first is invalid parent propagation. It's simple. If you build your block on top of a bad block, your block becomes bad too. This stops attacks from spreading. The second, bounded merge set, limits how many parallel blocks you can merge together at once. This stops an attacker from trying to hide a malicious change inside some giant messy merge. And the third, the kosherizing block requirement, makes every new block responsible for validating and weaving together the existing parallel history, which makes that history stronger with every single block that gets added. Altogether, these rules make being dishonest so computationally expensive, it's just not worth it.
Okay, we've been deep in the technical weeds. Let's pull up and talk about the payoff. Why go through all this trouble? Why does this really matter? The answer, in one word, is scalability.
First and foremost, it enables what's called trustless data pruning. This is huge. Because the network has a mathematical proof that a set of old blocks is locked in forever, nodes can safely delete that old data to save space. They don't have to trust some central authority, they can just verify the proof for themselves. And this prevents the blockchain from bloating to an unmanageable size over time. And that leads directly to the second major win, ultra-fast network synchronization. A new node doesn't have to spend days or weeks downloading the entire history of the chain. Instead, they can just download a very small, compact proof that verifies all that old, pruned history is valid. This means you can get a node up and running in minutes, not weeks, which is absolutely vital for keeping the network decentralized.
So you put those two things together, the ability to safely delete old data and the ability for new people to join the network quickly, and what you get is the foundation for massive, massive scale. Anticone Finalization Depth really solves the core dilemma for these parallel blockchains. How do you get all the benefits of parallel blocks without needing infinite storage? This is the answer. It lets the network grow and process a ton of transactions while keeping the hardware cost for running a node nice and low.
So, to wrap it all up real quick, Anticone Finalization gives us an exponentially strong guarantee that parallel history is locked in. It's a special concept just for these DAG-style blockchains. It allows for trustless verification, all thanks to a clever system of invalidation rules. And, most importantly, it is the absolute foundation for building a truly scalable, high-speed, parallel blockchain.
And that leaves us with one final, big-picture thought. You know, for years, everyone in this space has been chasing the Holy Grail, a network that's secure, decentralized, and incredibly fast. By solving this really unique and tricky security challenge that only parallel systems have, this innovation might just be a critical piece of that puzzle. So is this the blueprint for a truly scalable blockchain? Well, only time's going to tell.